esteemed faculty members, researchers, staffs, and dear students. We wholeheartedly welcome you all to the culmination ceremony of the first of its kind Advanced Analytical Instrumentation ILIS Operator Training Program. And also, we are happy to have, and also we are happy to launch the first technology content series from PI-RAHI with an idea behind catalyzing ideas, accelerating innovation, and connecting friends to the society. Giving a brief background of the program, which PI-RAHI in collaboration with ISTEM, that is the Indian Science, Technology and Engineering Facilities Map, has been conducting over a 3-day period in collaboration with SAIF, Punjab University, Chandigarh. We would like to highlight we have successfully conducted a training of around 30 candidates who were well trained across different instruments, including mass spectrometry, electron microscopy, X-ray diffractometer, TGA DSC, and finally CD spectrometry. This included expert talks in the first half of the session, followed by hands-on training and demonstration in the second half of the session. I-RISE is a flagship capacity building initiative at a national level under ISTEM Office of PSA, which is designed to empower lab operators, technicians, and early career researchers with hands-on training in operation, calibration, safety, and maintenance of sophisticated scientific and engineering equipments. With that, I would also like to give a brief information about a very unique technology colloquium series, which is first of its kind in the northern chapter. And PI-RAHI brings its flagship knowledge exchange platform designed to inspire conversation across academics, industry, and governmental organizations, which is at the intersection of cutting edge research, technology translational, entrepreneurship, and policy initiatives. It strengthens different aspects of the society by translating and strengthening innovation ecosystem and advancing deep tech research on the frontier technologies along with cultivation of innovation leadership. With this, may I kindly invite Professor Rajat Sandhi to deliver the welcome address for the day, please.
Good afternoon to you all. I'm delighted that we started with something 3 days back that was also a first event. First of the kinds, we started this iSTEM workshop in the through the clusters in the north of India. And this was the first workshop through PI-RAHI, first through all the clusters. We also have a distinction of starting first Colloquium series, and that too with a decorated scientist, Dr. Anindya Datta, who joined as director of Institute of Nanoscience and Technology, Mohali, which is an autonomous institute of Department of Science and Technology. So the institute pursues one of the flagship programs of India, that is nanoscience and technology. We see nanoscience is revolutionized the way we treat disease. We see nanoscience is changing, I would say, energy sector, lot of applications of energy science. And if I have to tell about Professor Datta, I would say he's been professor of chemistry at IIT Mumbai, again one of the top institutes of the country. And his work primarily focuses on uh, making or developing fluorescent molecules or nanomaterials which have applications in various fields, start of biomedicine, sensing solar energy, and conservation. So I'll not talk about his work because his work will be reflected while he talks about his contributions and his vision for INST. When he talks about his vision for INST, I would say that his vision would also get benefited. Along with that, I would say even institutions in this area or industry in this area would also get benefited. I particularly was impressed with something that is close to my heart. When I saw his CV, said he's developed molecules, fluorescent probes that can pick up organelles. So we are looking forward to working with him if we can exploit the technologies that he's developed in the area of organelle detections. And I would also like to tell you something. He's in a place which is SAIF of Punjab University. He headed SAIF in IIT Mumbai for many years, and that SAIF also became one of the great centers of instrumentations in Mumbai. And something which impressed me more, he was even associate dean student welfare. So switching between science and dealing with students is a very, very difficult thing. If you ask me, I would not be able to do it. So he has the capability of talking to you and your age. That means he can handle students also very well. So if you talk about his accomplishment, I will say he has been elected as fellow of Indian Academy of Sciences, one of the top academies of the country. Publications enormous, many PhD students graduate, many postdoctoral students graduate, and has been editor of many top journals in the field. And to talk of that, I'll just name one, Journal of Fluorescence, which is again a very important and high impact journal. With this kind of credentials, we are excited and looking forward to hear Professor Datta. And I would say we will all be like students here, listening to him, learning from him. And I would say take few things from his lecture because the nanoscience, again, the kind of field he's worked in has application in any field that we talk of. So we at from PI-RAHI side also would like to collaborate with INST, with him also to drive the research ecosystem and the innovation ecosystem in the country. Thank you, sir. And I'd like to welcome you once again. Over to you.
So the author letter to write research to Professor Meenakshi Goyal, Director of Research and Development at Punjab University. Professor Meenakshi Goyal is a distinguished academician and a senior professor at Punjab University. And I think when he currently serving as Director of Research and Development Division at university, which is a key office that promotes research culture, innovation and development across different activities in the institution. May I kindly request Professor Meenakshi to deliver the lecture? Here is this and next pleasure. We are here today on the occasion of knowledge colloquium and benefit function of the advanced analytic instrumentation I-RISE operational training program being organized from 18 to 20th February 2020. At the outset, I extend my warm greetings and heartfelt appreciation to the organization for hosting the highly meaningful and forward-looking program. I take the opportunity to respectfully acknowledge and welcome Professor Anindya Datta, Director Institute of Nanoscience and Technology, Mohali, our distinguished speaker for today, respected dignitaries on the dais, esteemed faculty members, scientists, and distinguished participants from academia and industry, and my dear students and young researchers who are the true torch bearers of tomorrow's scientific India. A very warm welcome to all of the theme chosen for today's occasion, reimagining technology, curiosity, creativity, and collaboration is not only appropriate but deeply inspired. We are living in extraordinary times where the pace of scientific advancement is redefining economies, reshaping governance, and transforming healthcare, strengthening industrial productivity, revolutionizing education. Technologies such as artificial intelligence, nanoscience, advanced materials, biotechnology, sustainable energy systems, and digital platforms are no longer futuristic ideas. They are realities shaping the present and defining the future. However, I firmly believe that technology is not merely about instruments, machines, or laboratories. Technology is ultimately about the human mind, about our ability to imagine, innovate, and create. It is about curiosity that dares to ask bold questions, creativity that challenges conventional thinking, and collaboration that transforms ideas into real society impact. These three pillars are the true foundations of progress. Today's program on advanced analytical instrumentation holds immense significance. In the modern scientific world, research excellence depends upon precision, accuracy, and the ability to generate credible and reproducible data. Advanced innovation is the backbone of innovation in nanotechnology, pharmaceutical, healthcare diagnostics, environment monitoring, material characterization, and industrial quality control. In fact, it is often said that a nation's scientific capability is measured not only by its publication, but by the strength of its laboratories and competence of its skilled manpower. In that context, the I-RISE operator training program is a commendable step towards building a technically skilled workforce capable of supporting world-class research and industrial growth. In the present era, innovation thrives at the intersection of disciplines. The most impactful discoveries occur when engineers collaborate with life scientists, physicists work with chemists, data scientists partner with environmental researchers, and universities join hands with industries and startups. Therefore, universities must not remain limited to knowledge dissemination. They may become engines of knowledge creation, innovation translation, and technology development. Research outcomes must not only be published, must, but or must also be patented, prototyped, commercialized, and applied for the welfare of the society. I am proud to share that Punjab University has been steadily strengthening its innovation ecosystem through focused initiatives in cutting edge areas. We have expanded our activities in artificial intelligence, data science, and emerging technologies through training modules and interdisciplinary research clusters aligned with Industry 4.0. Our faculty members and researchers have shown remarkable progress in patent filing, technology development, and translational research, addressing real-world challenges in sustainability, healthcare, and environmental protection. A significant milestone has been established of the INST Idea Lab at our South Campus, which empowers students to convert their ideas into working prototypes and fosters a culture of hands-on innovation. Equally transformative is PI-RAHI, the Northern Region Science and Technology Cluster, an initiative that unites academia, industry startups, and government into a powerful ecosystem.
PI-RAHI is a platform that supports interdisciplinary research, accelerates deep tech entrepreneurship, strengthens industry partnership, and promotes commercialization in domains such as medtech, clean energy, advanced manufacturing, and healthcare innovation. Through such initiatives, we are moving from isolated research to an integrated and mission-driven innovation framework. It is an indeed a matter of pride that TNRAD Northern Region ICT Cluster is presenting its first technology colloquium team including aspects of nanoscience and technology. Nanoscience is one of the most promising domains of the 21st century. Its application in electronics, energy systems, drug delivery, sensors, coatings, and next generation materials holds immense promise for both national development and global advancement. We are deeply honored to host today Professor Anindya Datta, Director INST Mohali. Professor Datta is a distinguished scientist and an academic leader as told by Professor Rajat Sandeep, whose work and contributions have significantly enriched the field of nanoscience and technology. His presence with us today adds great academic value and inspiration, especially for our young. I am confident that this lecture will not only provide deep scientific insight, but will also ignite curiosity and motivation among our scholars and students. As we come to the valedictory phase of the IOTP training program, I would like to congratulate all the participants who have successfully completed this rigorous and enriching learning experience. I also place on record my sincere appreciation for the coordinators, mentors, trainers, technical staff, and supporting teams who have worked tirelessly to ensure the success of this program. Such programs strengthen not only individuals' competence but also the collective research capability of institutions. Let me conclude by saying that the future belongs to those who dare to explore, imagine, and innovate. Let us move forward together, driven by curiosity, guided by creativity, and strengthened by collaboration to build technologies that empower humanity, strengthen our nation, and contribute meaningfully to the global knowledge ecosystem. With these words, I once again congratulate the organizers and participants, and I wish the technology colloquium a great success. Thank you very much, Jen.
Thank you, Professor Boyer. It was indeed an intriguing address on reimagining technology, curiosity, creativity, and collaboration, and sets the stage for the first technology colloquium series. With this, may I kindly invite Professor Anindya Datta, Director INST, to deliver the talk on intrigues and prospects of nanoscience and technology, please.
Did this work? That's what. Thank you very much. I'd like to thank Professor Sandeep for the kind invitation. Uh, this is the second time I am here in this room in a very short time. I've been in Mohali only for well less than 3 months, but I'm very happy that the community has extended such a warm welcome, which this region of country is well known for. So, Professor Sandeep, Professor Arora, Professor Goel, thank you very much for having me here. And I'm really delighted to be here addressing this gathering for several reasons. As you heard, I was head of Sophisticated Analytical Instrumentation Facility, SAIF, of IIT Bombay from 2016 to 2018. And in that capacity, I sort of became a union leader of all the SAIF heads across the country uh, for whatever reason. And then I had a second inning when I became head of the Center for Sophisticated Instruments and Facilities, which was a larger entity of which SAIF IIT Bombay became a part. Some of us would know that we received this really generous Institute of Eminence grant from the Government of India, with which we could set up as many as 180 central facilities in Hyderabad. But then, as Spider-Man has taught us, with great power has comes great responsibility. So somebody had to get the house in order, make sure everything is available for everybody, make sure they become sustainable. That was my job for almost 3 years before I came here. So SAIF is something that is very close to my heart. And this is an iSTEM workshop, I believe. Is there anybody from iSTEM here? They were there on the first day, okay. But they given an idea about iSTEM. Yes. So iSTEM is the national platform on which all instruments are supposed to be there. And well, for since January 2025 to December 2025, I had really intense interaction with the iSTEM people because I think there are only 25 persons sitting in a corner of IISc Bangalore. It is not very easy for them. So our job was to tell them how things had to be done differently, what is the problem we are facing. But iSTEM is a really great initiative that tries to make sure that a long-standing problem that we have had in this country, that people get grants for establishing instruments, and then they think that they have inherited it. It is not like that. Anything that is established by public money is for the public. iSTEM is ensuring that that happens. So this is really a great initiative from which all of us would benefit. Okay, today is, and I'm really honored to be speaking in the first uh, as colloquium in this technology series that PI-RAHI has initiated. I'm humbled. I was saying, after coming to Mohali, my general knowledge about these things has increased, I don't know how many fold, because earlier my job was to teach, do research, and take care of these things that they wanted me to. Here I see there is such an ecosystem in Chandigarh and Mohali. There's so many institutions, so many things going on. PI-RAHI is there. Punjab State Council of Science and Technology is very active. So this is really a great opportunity for all of us to join hands and uh, do something very new together, starting from fundamentals all the way to applications. Fundamentals are important. If you try to go into applications without developing fundamentals, well, then I'll not take the example. Everybody knows what has been going on for the last 3 years. That is going to happen. That's the day. Right. So I'll keep it very general. I'm an experimentalist. I do time resolved spectroscopy. And when I say time resolved, the time that we work with are femtoseconds, 10 to the power minus 15 seconds, to more recently we have gotten into microseconds. So it is a very data intensive, experiment intensive kind of research. But since this is a colloquium, I'll not uh, show you too much of data. I show you one or two just to show that we can go down to femtosecond. But I'll keep it very general and talk about something about which all of us possibly has some idea. That is nanoscience and technology, why it's important. We'll talk about one problem that we have been trying to address in our group and a little bit about what goes on in INST. And at the end, how we can perhaps do things together. Fine. So let me start with something that the all-time, the one president of India that everybody had very high respect for was him. And what he had said about nanotechnology was that when the materials are in nano regime, and this is put very beautifully, and it sort of summarizes the essence of nanotechnology and nanoscience in very few words. When the materials are in the nano regime, it opens up a very interesting challenge to basic physics and chemistry. All the properties change. By making the same material in the nanoscales, you could get materials with unimaginable and useful properties. What are the things that can happen if you go down? Okay, what is the meaning of nano? Nano means something that's very small, right? And giga means something that's very big. And when we talk about nanometer, we mean 10 to the power minus 9 meter. Yeah. So suppose, and perhaps the origin of all this comes from a very basic curiosity that humankind has had from the very beginning. What happens if I take something, anything, and start breaking it up? Where does it end? This is the question that led to the discovery of atoms and subatomic particles and all. And then, if you don't go that far, as we start breaking things, many, many new properties come up. The first, easiest thing that happens, as you all understand, is that the surface area increases significantly. So, we think of maybe a cricket ball, right? Most of the substance is inside, cannot see it. But if I break it up and make nano-sized materials, then whatever was there in the bulk would come out in the surface. So there will be huge increase in surface to volume ratio. And that itself, if nothing else, can lead to many interesting properties, like you can do catalysis on the surface. Yeah. Or you can use them as drug delivery media, as Professor Sandhi was saying. But it is not just this. You take gold and break it down and go down to the nano regime. Gold exhibits a particular kind of phenomenon called surface plasmon resonance. And that can be tuned by changing the size of gold. Conductivity changes, magnetic property changes, everything changes. And sometimes you get properties that you do not get when it is in bulk. I'll talk about semiconductor nanocrystals shortly. Now, this is uh, this very cliched quotation is often proposed to be the beginning of nanoscience and technology in modern times. In fact, this was said so many times in 2010, 11, 12, that kind of time, that I decided that anybody who shows this in their talk, I'm going to walk out. They were sick and tired of speaker after speaker after speaker after speaker saying, Feynman has said there's plenty of room at the bottom. All right, he had said it, understood. But, well, the thing is, that really is a profound statement. I'm sure many people have understood the case, but this is something that stuck. Also, because Feynman was such a great scientist and such a colorful character. Uh, whoever is interested, or maybe some of you read, he has some very strange books with strange names. One of the books is Surely You Are Joking, Mr. Feynman. That's the name of the book written by Feynman. And the other name of the other very popular book was What Do You Care What Other People Think? And they essentially tell you what kind of a strange person he was. If you have not read the book, I encourage you to read it. But for our purpose today, this is something that he said, which sort of inspired a lot of people to explore what is there at the bottom. But then, nanoscience and technology has actually existed from time immemorial. And uh, we are familiar with things that are in nano dimensions. For example, the bhasmas that have been used in Ayurveda for ages. Perhaps, I mean, we did not have the means to go down and see that they are materials, but they are. That has been explored in more recent times. And the reason why bhasmas are effective in some cases is that they are nanomaterials. Ayurveda is a very empirical science. So even though things may not be well understood, uh, centuries of experimentation led to things like this in those days. In fact, the oldest known example of nanomaterials was obtained during an excavation that took place in a place called Keladi, if I got the pronunciation right, some 400 kilometers from Chennai. So there, some earthenware was discovered. You can see this is a broken piece of a pot, and this is the inside. The inside you can see is completely black. Detailed analysis has been done, and it has been identified that this black thingy is really made up of carbon nanotubes. And the reason why they had it was that they used some flowers and used some material while firing the pot, which gave carbon nanotubes. These date back to 3 or 4 centuries before Christ. So 2300, 2400 years ago, it was already there. Once again, did they want to make nanotubes? I don't think so. But it was there. If you move back a few centuries, uh, Middle East Europe had things like stained glass windows in churches, and this once again is a very celebrated example, which people later realized involved nanotechnology. This this kind of a cup, it has a kind of color. If you put a light behind it, the color changes. That is because there are gold and silver nanoparticles on the surface of the cup. That is what is responsible for this kind of color. Finally, in nature, many of us would have seen lotus leaves. What happens is if you put water on lotus leaves, you get this kind of a drops. That's because the lotus leaf surface is what we now call super hydrophobic. And it's super hydrophobic because if you go down to the nano level and see, you can see the length scale here. This much is the horizontal line, that is 10 micron. So you can see these pointed things at regular intervals that are there on the surface. You cannot see them with your eyes, but here in this image you can see them. Not only that, if you look even more closely, you'll see at the tip of those pointed things, there are small spherical objects, right? Those are the uh, nanoparticles that are there, made up of wax-like material. That is what is there on the surface of lotus leaves, and that is what makes the leaves super hydrophobic, right? But then how do we see it? How is it that we can see an image where we say 10 micron and then we say that we can go even to smaller scales? We see it using uh, electron microscopes. I did not get good photographs of the INST microscopes. So these are actually from IIT Bombay, SAIF. This SAIF also has electron microscope. On the left hand side, what you see that is uh, TEM, transmission electron microscope. On the right hand side, we have scanning electron microscope. And these can be used to visualize the nanoparticles, but not only to visualize. In fact, as the nano research became a fad across the world, many people started working on it. And the problem with any quote unquote hot area is that thousands of people jump into it without understanding how exactly to go about doing things. So uh, I know of experts in electron microscope who get really annoyed because they say that people use these electron microscopes as a very costly camera just to get images. Electron microscopes actually do a lot more than give you photographs. They tell you about the arrangement, the composition, many different things. In IIT Madras, we have this electron microscope which was set up as a consortium of many institutions. It's called atom probe thermography, which means it can give you atomic resolution. So all this can be used for really high-end research and to take our research and our understanding to a level that was nowhere close to what was accessible even a few years ago. So one of the things that has become increasingly important is nanoelectronics. Well, I come from IIT Bombay, and it's a matter of pride that IIT Bombay has really uh, played a leadership position thanks to Professor Joseph Vashi, who got the Padma Shri Award this year. There is a nanoelectronics center, and there's something called IU, Indian Nano Users Program, where one can write a proposal. You have to say, because they are not going to uh, entertain people who want to use microscopes as cameras. So you have to write a proposal, say that this is the research I want to do. If it is approved, then you can go there, stay there, everything is free. Somebody will teach you how to do the experiments you want to do because it's not just seeing, right? You have to fabricate as well. The very high-end fabrication facilities are there, so you can actually spend some time there and do it. So nanoelectronics has become very big. And why is it that we care about nanoelectronics? Because we know that uh, the world is moving towards quantum computers. In fact, quantum computers are no longer in the future; they're there. Again, going back to IIT Bombay, I have a colleague there, young colleague, who got a grant from IBM of 47 lakh rupees and he did not get any money. He got usage time on their quantum computers. With that 47 lakh rupees, can you guess how much time he got on the quantum computer? 47 lakh rupees is a lot of money, right? It translated to 12 hours of machine. 12, 1, 2. But the idea is that in these 12 hours, if you are good at it, you will be able to do computation that would require maybe 3 years on regular computing. Now, if you want to really get into quantum computing, then your computer has to be small. All of us possibly have seen pictures of old day computers. One computer would be of the size of this room, and it would have computation power less than what we have on our cell phone today. Yeah. Or this 512 megabyte hard drive being taken out in a trolley. That's a very famous picture, right? That is where we started from. But then when devices are bulky, there are many problems that come in. Heating is an issue. Components going bad is another issue. So there has been a huge thrust on miniaturizing things, and that is why you need nanoelectronics if you have to achieve quantum computers, right? And successfully use AI. Those of us who follow the news would know that it's a matter of happiness and pride that a couple of weeks ago, a 2 nanometer chip was launched in Bangalore. Well, it is made by Qualcomm, which is a foreign company, but this is a design in India chip. A significant amount of effort is going into making these nano chips and all. And there, Chandigarh has a role to play because Chandigarh houses the semiconductor laboratory, right? So perhaps uh, those of us who are of my age group or something like that would know this was a great promise that's unfortunately hit a roadblock because of a fire that took place in 1997. Something it was arson, something it was an accident, we don't know. But had SCL grown at that time, nobody knows where exactly in the world map India would have been today as far as semiconductors are concerned. But then, significant amount of funding has now been put into SCL, and Chandigarh will have a role to play in this effort, which will take us into nanoelectronics. Nanomedicine, as Professor Sandhi said, is another area that has seen very active research across the world. Because one can tune the nanoparticles in such a way that would go and target organelle. Secondly, the surface area is large, right? So one nanoparticle can actually hold many, many drugs. So you can give a high dose of drugs using nanoparticles and it would be delivered exactly where it wants. So precision medicine, as it becomes a thing of reality, nanomedicine will play a bigger and bigger role. This is where INST has put in significant amount of efforts. These are some examples of what our colleagues in INST have done towards nanomedicine as well as healthcare. The newspaper article that you see, that is about a watch that has been developed by one of our colleagues. You put on the watch and it sort of diagnoses. You don't have to prick or do anything. And he has now modified it so that it can be used on newborns as well to follow several complications that come with nanotechnology for agriculture. We are in Punjab, so this is something that would be of great importance to all of us. And the reason why this is important is, first of all, nanofertilizers, once again, like the nanomedicine, can be used to increase the crop yield significantly. But it's not just uh, nanofertilizers. So this uh, scheme here tells us the different areas in which the which nanotechnology can contribute or research is being done to explore the possibilities of nanotechnology in agriculture. Crop protection is one. Crop packaging is another. Uh, we have electron transfer thing, pesticide, fungicide, herbicide, nanofertilizer, controlled release, so on and so forth. These are the areas in which one can use nanotechnology for agriculture. And this is an area that I think is explored much less than what it should have been in this country, in this state, in this city. This is where I think we require a concerted effort. Perhaps PI-RAHI can play a role in catalyzing it. where we have Navi in Mohali, right? Navi, as Professor Grover told me, is supposed to be the TIFR of agriculture, and it's actually going in that direction. In our institute also, we have a couple of people working in this area. This is these are a couple of examples. First paper that you see is about nanofertilizers. They have used what is called MOF, Metal Organic Framework. Last year's Chemistry Nobel Prize, you may remember, was on Metal Organic Framework. Uh, so they have used Metal Organic Frameworks to ensure that the whatever medicine, fertilizer, whatever is delivered actually sticks and doesn't fly away from the intended areas of the plants. This is a work that has come as a collaboration of Vijay Kumar Shanmugam is from INST, Nitin Singhal is from Navi. So this is an example of what inter-institute collaboration can do that we cannot do by ourselves. And this is what should be happening more and more, especially in the ecosystem that has come up so nicely in this area. The other paper that I want to highlight here, again from INST, was that they made a gas sensor because in agriculture, lots of gas, if you, fertilizers have a smell. So anything that has a smell contains volatile substances. And sometimes you cannot smell it, but it is either good or bad for the thing. So you need sensors to know whether what is the gas content of the soil or whatever it is. So this is another area that is being pursued in INST. Now coming to the work of our group, we are very interested in quantum dots. Quantum dots are nanocrystals of semiconductor materials. So what happens there is that uh, well, we have all studied about conductors, insulators, semiconductors. If it's an insulator, so all solids have this valence band and conduction band, right? So if it's a conductor, then there's no band gap. If it's an insulator like silica, there's a huge band gap. If it's a semiconductor, then the band gap is somewhere in the middle. And since we are spectroscopists, we always think in terms of light. The band gap is typically in the ultraviolet visible range. Now, going back to the question that we asked earlier, what happens when you take something and start breaking it up? Suppose you take a semiconductor, cadmium selenide, cadmium sulfide, uh, gallium arsenide, and start breaking it. When you go down to, say, 10 nanometer scale or a little less, something interesting happens. Solids, as you said, have bands, right? When we go down there, it is still a solid, still particle, but within the conduction band and valence band, discrete energy levels come. So they also start behaving like molecules in a way, right? And I show you one equation that explains it, and then many different things can happen which don't happen in the bulk solid. So again, if you think of applications, quantum dot is no longer a subject of just fundamental curiosity. They have been used to make solar cells. This is a photograph that I took in 2022, if I remember correctly, in Mumbai airport. And if you read what is written at the bottom, I don't know how clear it is. You see, it says QLED, which means quantum dot LED. Some of us may have QLED TVs at home. So it's there in the market, it's being used already. And this is one application in electronics. The other application is quantum dots are usually photoluminescent, they give out light and they're very brightly colored. So the second application is biology. Here is an example where quantum dots have been injected inside mice and they are being used as reporters for the health of the mice. So this is what got us interested. Sometimes people get surprised when we say that we work in the area of materials as well as bio, and they think what is going on. Well, this is what is going on. Material that we work with actually has applications in electronics as well as in bio, and we are curious about both. So one very interesting phenomenon that is there of quantum dots is that you take the same material, say cadmium sulfide, make quantum dots of different size, they have different colors. And that is governed by this equation, which was given by Professor Bruce, who got the Nobel Prize in chemistry in 2023. where you see the terms that are there. The first one is Eg infinity, that means the bulk band gap. Last, we have minus 1.8 e squared divided by epsilon capital R. R is the radius of the quantum dot. And the second one, those of us who have studied a little bit of quantum chemistry or quantum physics would recognize that this is the energy expression of a particle in a box. Here, the particle is the exciton. Exciton means when you do an excitation, the electron goes to conduction band and a hole is left in the valence band. Electron is negatively charged, the hole is positively charged. So they are correlated. They move together. Together, they make what is called a quasi-particle, and the name that is given to it is exciton. The meaning of ton in this case is unit. We know electron, right? Electron means unit of charge, smallest charge that you can have. Similarly, exciton is the smallest amount of excitation you can excite. So this is the thing. You don't need to use different chemicals. Same material of different size can give you different colors. And these colors that you see are all photoluminescence. You can see the background is dark, which means this has been placed in ultraviolet light and it gives out this kind of color. And when you make excitons, by you have shine light, electron goes into the conduction band, hole is there in the valence band, exciton is formed. Then what happens? One thing that can happen is that they recombine and give out the light and show you that color. But then, depending on where you are excited, many different processes can take place. And these processes take place in time scales of femtosecond to microsecond. So, with many years of sweat, blood, tears, etc., we have been able to set up all these facilities in IIT Bombay. And uh, one of the motivations for me to come to INST was that almost all of these are already there in IIT. In fact, there is this instrument called transient absorption. INST transient absorption is better than IIT Bombay transient. So, uh, with these, you can think, without going into further detail, these are our stopwatches. So, when there's a race, stopwatches are used, right? And that gives you sort of millisecond kind of resolution. These are our stopwatches, without going into the detail, that give us resolution up to femtosecond or picosecond or nanosecond, depending on what we do in that particular experiment. So we studied exciton dynamics in quantum dots. Uh, we learned how to handle them and so on and so forth. Then we started thinking, how can we use quantum dots to do some chemistry? And that is when this field started breaking off again. Carbon dioxide reduction is another hot area that everybody wants to work on nowadays. Uh, if you think like a chemist, what are we trying to do here? Well, it is there in the name also, carbon dioxide reduction, right? It's a reduction process. Means you have to give an electron. How is this brought about? Most of the time, you have a catalyst. And conventionally, the catalysts that have been used, as you see in this figure, are porphyrins. Cobalt porphyrins have been used extensively. What they do is, since it's an aromatic system, so many electrons are there, they donate some electron and the reduction is brought about. So we did not start this field. As you see, I'm showing somebody else's paper to start with. What got us interested in this was what is just about started at that time, photosensitization of catalysts for carbon dioxide reduction. What does that mean? Well, what is the job of the catalyst? To give electron. We want to do reduction. If I can somehow pump electrons into the catalyst, then it should become a better catalyst. Right? I say, please say yes, no, something. And if I can do this pumping of electrons using light, that opens up the field of using solar energy to do carbon dioxide reduction. Two birds in a stone. Yeah. Here, quantum dots are very good candidates. First of all, they have large surface area. So what can happen is you add quantum dot, add molecular catalyst, the catalyst can go and stick to the surface. Right? You don't have to do any chemistry for them, just mix. Secondly, quantum dots usually have very broad absorption. From UV to red, sometimes NIR. So it can absorb a lot of sun. Finally, going back to the same hand gestures that I showed you twice already, we have valence band, we have conduction band. So when light falls on the valence band, electron goes to the conduction, right? So that means you have energized the electron. You have heated up the electron using light. Now the electron can go from there to the catalyst. Those of us who are students of chemistry will be familiar with the term occupied and unoccupied molecular orbitals. So in case the energy alignment is such that unoccupied molecular orbitals of the catalyst are there, just a little less energy compared to the edge of the conduction band, then what will happen? No electron will go in the ground state. But when you excite, electron will get transferred from the quantum dot to the catalyst. This is called photosensitization. Photosensitization is a very common technique used in biology also. So in this paper by the group of Professor Emily Weiss, who was in University of Chicago at that time, now she is in Northwestern University, they used copper indium sulfide quantum dots to sensitize this cobalt porphyrin, and they had a turnover number of more than 80,000. Turnover number means number of moles of product divided by number of moles of catalyst. 80,000. One catalyst is giving you 80,000 uh, one molecule of catalyst is giving you 80,000 molecules of CO2. So the problem is we never did catalyst before. Catalyst before this. And unfortunately we read this paper first. So this number 80,000 stuck to our mind. We thought if it is 80,000 then it is good. If it is not 80,000 it's not good. So for 2 years we did something, we got some results. We kept thinking utna acha nahi hua. Then in November 2024, I organized a one-day workshop on photocatalysis. Experts in photocatalysis from different parts of the country, one from US came and happily talked about the turnover numbers of 200, 400, 500. Then we realized that our numbers are not. I'll tell you what the numbers. All right. So we started working with copper plus doped cadmium sulfide quantum dots. We are working on them already for some other reason. Happens is you take a quantum dot, cadmium sulfide, and you manage to do it with very small amount of copper plus. Very small means on the average no more than one copper plus ion per quantum. What we observed is if you put too much of copper plus, then things get messed up. Now copper plus, remember, copper plus, generally when we work with copper, what do we think? Either metal copper or copper sulfate, copper 2 plus, right? So copper plus is not all that common. Copper plus wants to become copper 2 plus. How will it become copper 2 plus? By giving away an electron? Or if you think the other way, by taking up a hole. So when copper plus doping is done, what it does is you shine light, again, for the fifth time, electron in the conduction band, hole is there in valence band. So energy alignment usually is such that copper plus energy level is there very close to the valence band edge. So it takes up a hole from the valence band. Now what happens? These are all wave functions. Don't get scared when I say wave functions. I'll not write any equation. The electron wave function is spread all over the nanoparticle. The whole wave function now, when you do copper plus, is localized on that one copper plus ion. Now it is copper plus. So spatial overlap is destroyed. Yeah. So spatial overlap is destroyed. Electron and hole cannot recombine so easily. Or you can think like this: electron does not feel the electrostatic attraction of the hole so much. So our question was, does it make the electron easier to give away for the quantum? So now it is not being held back so strongly by the hole. So we did the experiments, and we of course we are not catalyst people, so we collaborated with uh, once a student of our department, now a very celebrated professor, Anindya Datta. Sometimes Datta collaborating with another Datta sometimes creates confusion. And their group used to steal our nitrogen cylinders also. Because AD is written on the cylinder. So they happily taken, I don't know where the cylinders are. So since they're stealing our stuff anyway, we decided to collaborate with them and make the most of it. And the good thing is we have complementary expertise. We are ultrafast spectroscopists. They are people who can make catalysts and who can also do this catalysis experiment. So this is a video. I don't know whether it will run. Let's see. It doesn't look like once you do this. So just believe me that that is a photocatalysis chamber. So what we did is we told them you'll do the photocatalysis eventually, but before that, give us some bad catalysts. See, a deficiency is always an opportunity. Right? If it's already very good, how will I improve it? So they gave us these two complexes, one copper complex, one iron complex, which apparently work well in your non-aqueous medium, but doesn't work at all in water medium. I'll show you the data. So our challenge was in water, can we do carbon dioxide reduction? Can we do hydrogen evolution by photosensitizing them with our quantum dots? And does copper plus doping make the quantum dots better? Here is the answer to that. Now, if you look at the x-axis, it's 8,000 and 4,000. These are the numbers that for 2 years we thought were bad. They're not bad, they're very good. Yeah. And you can see the top curve is for the copper dope cadmium sulfide quantum dots. The bottom curve is undoped quantum dots. You can see undoped number is more when we do copper doping. So the goal with which we started, that we'll do copper doping and it will become a better photosensitizer, that is here, right? But we didn't stop there. The thing is, nobody wants to work with cadmium. I don't have to tell you why, right? So the focus is on carbon on quantum dots that don't have heavy metals and all. So we switched to copper indium sulfide nanocrystals, and we used two of them. One was bare nanocrystals. They were not very good because this is the fluorescence spectrum. You see, this is the fluorescence spectrum of copper indium sulfide quantum dot. It becomes so much stronger if we put a coat of zinc sulfide on it. So it's like a core shell nanocrystal, core shell quantum. Now, the question that we had was the reason why uh, photoluminescence shoots up is that zinc sulfide does what is called surface curing. There are many defects on the surface which lead to non-radiative recombination. Electron will recombine, no light goes on. So that is cured. So that seems to be good for photocatalysis. The problem is now once we put a shell, the electron has to go through that shell, right? It would invariably become slower. So the question was, which effect wins? When we put a zinc sulfide shell, surface curing happens. Does that make it a better photosensitizer? Or does it make it a bad photosensitizer because the electron now has to go through that zinc sulfide shell? This is one piece of data that I show. You can see in x-axis, it is some hundreds of picoseconds. So from this experiment, we can find out the time required for the electron transfer, photoinduced electron transfer. 1.8 picosecond for the bare quantum dots, 3.4 picosecond for quantum dots with a shell. So this is what tells us that zinc sulfide shell does slow the electron down, right? But this is what we get for the turnover numbers. This one is the catalyst alone. I told you it's a bad catalyst. This is the catalyst photosensitized by bare quantum dot, copper indium sulfide only. This is the plot for uh, photosensitization by copper indium sulfide with shell of zinc sulfide. Now we get numbers of 17,000 turnover number. Why is it so? I already told you one reason, that surface is cured. Let's not go into that now. The other reason is this. Okay, you transfer an electron, fine. Your expectation is that now the catalyst is going to transfer that electron to carbon dioxide and reduce it. But don't forget, the catalyst is sitting on the surface of the quantum dot. It can give the electron back. That is called back electron transfer. That is a much longer process. Now, if you look at the x-axis, it is 400 nanoseconds. What we see is that, see, zinc sulfide slows down an electron going through it, irrespective of whether it is going from inside to outside or outside to inside. So this back electron transfer is hindered very, very significantly. That is why the catalyst can gets a chance to do what it is supposed to. So there are two reasons, not one. All right. So we are now looking at a library of quantum dots, library of uh, catalysts, and also a library of reactions. We don't want what reaction we have done earlier is carbon dioxide to carbon monoxide, which always scares. Carbon monoxide is a poison. But we are trying to do other reactions as well. And Arnav is sort of an entrepreneur. He has a company now. He has promised that he will teach us how to make a prototype out of it. So let us see whether we can go to the prototype scale in maybe a couple of years. But this is the beginning. So one point I'd like to emphasize is this. I said it already. See, fundamental curiosity and applications have to go hand in hand. We cannot suddenly say that the demand of the world is this, therefore that is what I'll work on, even though I'm a trained uh, sociologist. We cannot do that, right? We have to play to our strengths. So one thing that we are interested in, as I told you, is biology. And this is a paper that has really triggered our imagination. Somebody else's paper came out in 2025. If you see the cartoon, it looks like a carpet and a couple of sausages on the carpet, right? So the carpet is not a carpet. It is really many quantum dots that have been put together. And the sausages are also not sausages. They are microbes. So what is happening here is that same technique, photoinduced electron transfer, is being done. And the electron is now going through into the microbes and initiating a reaction. So the microbes are being used as bioreactors. And these things that you see here, they are images recorded with fluorescence lifetimes, not intensities. One thing that happens here is that electron transfer becomes much slower. From picosecond, it goes to nanosecond. So this is something that has really triggered our imagination. We want to see whether we can get into this photo-induced bioreactor business. Well, we have never worked with microbes yet. Now, as a Sunday, what we have done is we have worked with cells. Uh, I don't have a photograph here, but here she is. Dr. Srishti Pandey is a postdoc that we had for telling our colleagues here before coming here. I don't know biology. I did not study biology even in 11, 12 because I was scared and bored and all. But slowly we developed a curiosity. So we really want to work on biological problems I don't know how. So fortunately, we got this postdoc who came from our background, and she has now taught us how to handle live cells. We have learned, and this is a molecule that has been synthesized in our lab by a very good student. So using this molecule, you see the images on the right hand side. These are again fluorescence lifetime images. We have been able to follow using fluorescence lifetimes a process called ferroptosis, a ferrocyan induced programmed cell death. So now we want to see, at least in cells, can we do something similar where we have a reaction going on inside the cell as per our demand, and we have got help. We started it in IIT Bombay. IIT Bombay has this joint PhD program with Monash University. So I'm collaborating with Toby Bell and Senthil, who are faculty members in Monash. We have recruited a joint student. Uh, so we are really excited about this project. The other thing we're excited about is the other end of the spectrum, from biology to physics or maybe electronics. Again, this is a paper that came out in 2025. The phenomenon is same. The system is same. Quantum dot, molecule, photo-induced electron transfer. But they have doing some additional experiments. They have been able to show that the spin information is retained. So this could be a step towards making qubits that are required for quantum computers. We have not understood this very well. We are reading, but we really want to get into this area as well. So everything that we have been able to do has happened thanks to this very bright, enthusiastic, good students and postdocs that I've had. Here you see people who joined our group, I think 2017 onwards. They are very close to each other. They have formed a ghetto. They have removed everybody else's photograph and given me this. And now that I am in INST Mohali, let me tell you a little bit about the institute, 2, 3 minutes. We have three major institutes with names that sometimes we feel scare away students. Because the names are EEU, which is Energy and Environment Unit, but it is essentially chemistry. Most of the faculty members there are from chemistry background, they work in chemistry. There is one unit called QMAD. Sounds very nice, quantum madness or whatever, but actually it's not quantum madness. Quantum materials and devices, essentially physics and little bit of engineering. And chemical biology unit is the only unit that has the same name, which everybody would understand. And this is our beautiful institute building, which is actually very well endowed. And very quickly, the areas in EU that one can work on are, where people do work on, are energy conversion, environmental remediation. People make sensors, and they also make devices. So it is going from chemistry to a little bit of physics with application in biology. That kind of research happens in EU. And we have a very significant number of very good faculty members uh, in all the three units. In QMAT, uh, this is the strength, mostly physicists. They work on, we also have theorists, there are three theorists. Computational nanoscience. And these people work a lot in things like AI, quantum computing, so on and so forth. Quantum materials. Well, AI, quantum sensing, I've already said. Advanced functional materials, spintronics. Spintronics, again, important for quantum computation. People make devices, wearable electronics. I told you about the watch. Then, microfluidics is an area in which you can have very small amount and you can get stuff made. And this work on piezo electricity is going on really very well. Finally, in chemical biology, these are the major verticals, but even though there's a lot of overlap, therapeutics, diagnostics, biomaterials and tissue engineering, agriculture innovations, and understanding biomolecular events at nanoscale. So if you go and read the fine print, it's like structural biology, regenerative medicine, nanotheranostics, uh, so on and so forth. So lots of areas, lots of applications of nanoscience and technology in different fields. Very good research is going on in our institute, and it's extremely well endowed, surprisingly well endowed for an institute of that size. Our sanction strength is 40. Right now, we have 36 faculty members. So, what I wanted to end with is we are now recruiting students. The PhD admission advertisement has been published earlier this week. This is the link. One catch: at this time, you can only recruit students who have qualified NET and have their own fellowship or Inspire Fellows. There may be some project positions available for others as well, but I do see students here and their faculty members. My request to you is please spread the word. This is really a good place to do PhD, and please encourage people to come to us. I'm sure they will have a very fruitful stay and they'll do very good research with us. And I invite everybody to visit us. We'll be very happy to host you in our institute. Thank you very much.
Insightful talk. We definitely learned so much from your talk, sir. You can ask to take a few questions for sir.
Encourage students to ask questions. Yeah, I can do the icebreaking. We talk about this turnover number, and one number you gave was 80,000, and no study showed 17,000. When I look at enzymes sometimes work in that kind of range. Exactly. So that means at times we can think of enzymes replacing. Yes. So back at least replacing enzymes. Actually, that happens. The thing is, here we wanted to use light also. So there are enzymes that are triggered by light as well. That's one thing. And secondly, the problem with enzymes that is there to a little less extent in quantum dots is enzymes die easier. Nanocrystals are little more rugged. I had one more question we will ask. So you talked about this probe that you were saying can look at ferroptosis. Did you try to create this molecule or not like on the, I see a lot of not clearly potential in this molecule. Clearly, possibly we can. That could be something that I was thinking. Yeah. That would have a lot of interest. Thank you. We really have never thought in that direction, but thanks for the suggestion. We may take it up. Maybe now, so, like that. I think he said a lot of things which were of interest. To us also, as PI-RAHI from my personal vision, the transient absorption. So what you do there is you excite whatever you are looking at using an intense laser pulse, which is of duration of say 100 femtoseconds. So what that pulse does is
promotes a lot of electrons to the conduction band. Or if you're thinking of a molecule, promotes many, many molecules to the excited state. And then there is another weaker beam of light that goes to the sample. That is where you look at the spectrum. Essentially, you see how what the dynamics is of change of the spectrum over time. From there, one can calculate all kinds of angles. Maybe different than the free electron laser. Free electron laser just gives you the light. So, in principle, free electron laser can be used as a pump. And this is a complete experiment. Good thing about free electron laser is that it can give you whatever wavelength you want. You said that now available here. Not free electron laser, pump probe is available. Yes. Yeah. Free electron laser, as far as I know, is there only in RRCAT Indore. In fact, they invited me. I went there last month. Now they have the free electron laser in different phases. They are getting different ranges of wavelengths. Now they have got terahertz and IR as well. The Rajaramana Center for Advanced Technology, Indore. It's a separate facility. It's not part of the center. The group director is Professor Dr. Shubhan Majumdar. So he has been in biomedical application section for a long time. Now he's. I see. Okay, that's great. Great to hear because I have been a visiting scientist in other cat for years. You can introduce yourself also because he's a professor faculty in chemical engineering. Very nice to hear that because I saw Indus 2 coming up. Yeah. I was there as a visiting scientist. My students are visiting there. Excellent. Yes, the same time for the next. That's a major Indian success story for Indian science and technology. Now we have not one but two synchrotrons. And even Indus 1 after the initial hiccups is doing very well. Also, yes. I don't know who is this. He is started also with PI-RAHI. This is funded by the program of Punjab State Council. Okay. I heard about that program recently. Yeah.
So when we talk about translating research into the actual products, actually the people are not so general. So you were talking about the nano fertilizers. Fertilizers are a valuable option. The current state. I have my own project of nano fertilizer and try times the it. But I it was the way. Because the industry are not that
That is no secret. Indian industry, unfortunately, doesn't care for R&D. That's how it is. It's a harsh truth, but truth nevertheless. Many years ago, when I was a PhD student, 95 or something, there was this science congress that was held with the express intention of bringing industry and academia together. Who's who of industry were there? And one of them said, if you can do our QA/QC, great. Otherwise, forget it. We are not interested in it. But things have changed. Uh, it is possible that an established industry all will not come. But there are so many ways to get funded. PI-RAHI, they can help. I'm sure anything. There are engineering investors. There are several government schemes. So I think the situation now is much more conducive than what it was even 10 years ago. Of course, the path is difficult, and I have only an outsider view of it because I never tried to do it. But yeah, I mean, कोशिश करने वालों की हार नहीं है. That's not interesting. That is they will collaborate with us and we will take that forward. So there is an incubation center there. Unfortunately, the problem is this INST is actually society. And the society cannot own section income. So there is this strange legal problem that we don't understand. We are trying to work around it and we are discussing with PI-RAHI. So the idea is that in collaboration with maybe IIT Mandi, with PI-RAHI, we can get that going, then it can be a very major boost for a lot of
I have a question of you in terms of this nano fertilizers. The consume, where is the thing you see in the problem is for success? Because the consumer, now my problem is the application. I need to have a pump to spray. As far as the threats are concerned, you just have to see that nano India or nano DKT, because that just pick up a handful and just split and you get the results in a couple of days. Here I have to throw for a pump, create a mix and kind of thing. This is like, it will be one and feedback on them for engaging people like technology when it comes, it is more expensive and definitely less popular because people are used to something is working well for them. Why will it? So that is where the challenge is. If you want to go from lab to practical application, one needs to first of all beat the state of the art. As you said, I mean, if urea works, why not? No, no, no. The point, no, no. Point is they're pushing nano urea now. Don't get it in regular market. You have to go to specific market to get the urea granule. I understand. Is available nano urea very easily, and I was like, bigger background was more keen on that. When subsequently applicant spraying that would be challenging. So it is like something you guys can, so get be better than. The farmers regularly at the large scale farmers they carry pumps, they have a problem that I agree. At the same time, this is point taken, and this is something that one needs to work on. And availability, it's like skin. So this is something given a suggestion also to us. Actually, yeah, more key in the nano, DAP, nano India using the good and arrow than for everything. Availability is definitely an issue because mass production and making it available in small scale. So these things have to be dealt with, and that is where, I mean, scientists and that is perhaps where it gets out of the domain of scientists and goes into the domain of industries, who are the ones who have to market it and take it everywhere. Yeah, I agree. Maybe a good question. You getting spiked. Yes, because the mostly is like already concerned. How are you going to arrange studies are going on, and once again, for a study like that, it is not just science. You need to perform surveys that go beyond the realm of what we can do, and so like, and nothing. There's no free lunch in this world, right? So as you say, Punjab is suffering from green revolution, right? But had green revolution not happened, people would have died. So I mean, the medicines are better than what they used to be earlier. What that results in is the average life of a person has gone up. I think perhaps it has doubled after independence. So now we have too much of population. So always there is, with any solution comes a problem which one has to address, and that addressing cannot be. Right. So with the aspect, with every solution there are some problems. The advent of the field of nanoscience, there was a lot of hype about putting everything with nanoscience. And then slowly, through workshops and talks, we also saw a new concern in the field where people were talking of leaching of those nanoparticles into the environment and now moving into macro pollution to micro and nano pollution. So how these concerns are being addressed by the team in the institution. So once again, mitigation is a
another vertical of research that you do something. Now, what do you do with the stuff that is left behind? Like, the reason why people don't die of hunger across the world is the Haber process, making ammonia, right? That is what led to so many fertilizers coming out and all. But then people are trying desperately to not do things by Haber process anymore because too much of problem is associated with it. So it's a challenge. One has to address it, and there may not be any easy solution. That is what is important to understand. And you used an important word also, that is hype. It is important to understand that whenever there is a new field, there is a lot of hype. And as I said, people just jump on the bandwagon. That is not the way to do research. One should not jump into whatever bandwagon comes our way. One should think, see, research, end of the day, is all about getting excited. What is it that excites? That is what I'll do, right? There was a time when I found biology to be boring. That's why I did not study it. And then I took this course in biochemistry and I started seeing the logic. That is when I got interested. That is what I should be driven by. If from the beginning, if I think that biology is the field where there's a lot of funding and I should work there, then things don't work out. So it is important, first of all, not to work in an area just because it is good. Secondly, again, with great power comes great responsibility. One needs to think of mitigation as
Still encourage students to ask the questions. It's indeed an exceptional opportunity that you are getting to interact with, sir.
I don't know, we can have some young minds, future of okay.
well. Sometimes they're shy, yeah.
So, we've been working with you for this time and for the work you are getting. If I am like more interested in it, if I go about it. So, is there any like way that I could connect to you later on or visit the institute?
That's my email ID. Write me an email, I promise I'll answer.
Thank you. One more question is encouraged.
I think
Yeah.
whoever wants to talk about anything or ask a question or something, please write me an email. I'll be happy to respond. After
this amazing talk, may I please request Dr. Meenakshi to felicitate Dr. Datta? Now I request Dr. Arora to please felicitate Dr. Meenakshi. So before we move towards the closing ceremony, I'm sure we all had a great time here. May I please request a few amongst us to share the insights, the fun that we had here, the learnings we had here. It'll be great to hear from you all. Whoever wants to go first. Yeah, please.
It's yours.
Thank you. Thank you. You want? We need a few more feedbacks so that we can know how we did and perform better the next time if we lag someplace. Go ahead. Go ahead, guys. Please come on. Yeah. Yeah, please. Thank you. Few more feedbacks will be amazing. Yeah, please go ahead. Yeah. So, yeah, with masters in microbiology. Let know about this workshop. What was really exciting because we were able to learn so many instruments, so many highly sophisticated instruments within a span of 3 days. And personally, I love to get insights into things like things for free. So learning the actual insights for self-help right? Actually like when the experience and moreover organizing team volunteers they really played a big role in this organizing who like played a part in it. I did see one more hand for a feedback. Thank you. Thank you. So, anybody else wants to go in? Okay. Before bring this come from far, are also can know what to use students or into give feedback. I think there were people from far off in the states. Like to have good. Thank you so much. Now I'd like to request Dr. Sanjeev Gautam, who's a faculty, a professor at our own university, Punjab University, to come up here and sir, please share a few words with us so that before parting, we do take some more amazing things with us as well. Thank you. Thank you.
Thanks. I again thanks for the very nice talk. It was actually my field, quantum dots, and I worked on this electron and hole decay in sometime in XFEL in Pohang Accelerator Lab. So I was very much interested in this work. This work is very good, especially for the catalyst and super catalyst thing. And especially they discussed about I I stem I-STEM thing is very good. Usually, as the sir has said, that for a long time we purchase some instrument from the DST and we think that okay, we have got something which I can get many papers by collaborating through it. But in fact, and after some time, it dumped because I don't get the money for the repair and everything, and the money got wasted. So this is very good that we have some instrument through DST or some another funding. We put it in the network. We get the repair and maintenance. This thing is being utilized, and it is a good use of the money that is a government money. As sir has discussed, this is a very good thing. And as this workshop, you people has learned to use the instruments yourself. That's a very good point. However, what we do, we send the sample to the XRD, and what students do, they even don't draw the data to the origin. They just take a picture, they put a picture, and they don't index it. So I think many of you has learned to do XRD, to do SEM by yourself. And also, I hope you have learned it about this, how to analyze the data, how to interpret that data for a better application. And as Madam has said, that this research should go to the technology, go to the use, again, not only the papers. And this, I'm very nice to hear about this, about workshop and other information that sir has shared. And I congratulate Professor Rajat also for this great initiative. Thank you. Thank you. This is something I'm just going to make to mention all the participants. We said in the very beginning, at the end of it, you should be able to employ all technique from this workshop into your research. That is the purpose. If you train think of it, you can do it actually. So there would be definitely a technique from here which you can employ, and then this is not the end of it. Come back again, CLA, the staff is it's a friendly facility. They encourage you, and if you're short of money, also you can find a can do that. Thank you.
Thank you. Thank you. Now I request Ms. Neha Arora, COO PI-RAHI, to please present the vote of thanks. Over to you, ma'am. Thank you so much, Professor Datta, for taking out your time in such a busy schedule. And me being from an MBA, also I think was able to capture a lot of things. So I would say commendable part. The way you explained is beautiful. I think the words comes articulated in such a beautiful manner. Thank you once again for coming out here. Thank you, Professor Goyal, for taking out your time and in Punjab University where we act as a beacon for research and translating into translating the research is where PII stands. So all in together, thank you once again. And thank you also to the PI-RAHI team who has been working from the past days and working towards it. All the volunteers who came from, I remember the institutes, Shimla University, Amity, and multiple others who came from Chandigarh. Thank you. And as Professor Sandhi said, please ensure to implement this. Don't take this as a workshop. Try to implement this in terms of the day four, that you have. You have eminent people here who are ready to help and support, but the effort has to be done from your side. Thank you for all the faculty who has come and joined out here. With that, I would say all the best and hope we are able to have much more Colloquium series. And I would say also to each and everyone, please follow PI-RAHI page. We keep on doing such exercises. So to ensure that we deliver the best, your support is also requested. Thank you, Neha. And before we move on to the next TA networking session, I would also like to acknowledge few students probably without whom the workshop would not have been a success. Their support would have been extremely useful throughout the workshop. Of this, I would especially mention Ms. Ria, Ms. Kirti, Ishita, Tanisha, Preeti, And Raghav, I think for every workshop which PI-RAHI does, they are the cornerstone standing by, making all the events a big success. With this, I also thank the participants for making this event a big success, and we look forward to welcoming you again at PI-RAHI in Punjab University. May I kindly invite everyone to join us for the tea and networking session, and post that the participants will be given the certificates for the workshop.